speaking. All right, ideas for the first one. Yes.
I first factor out the denominator.
Okay.
So you can consider as a cubed plus b cubed. So the denominator I factored it out to x minus 1.
It'll be x plus 1.
Sorry, x plus 1.
And x squared minus x
X
plus
squared
1.
minus x plus 1.
Okay. And then? And then you try to do a partial fractions? Yeah. What did you
Find a equation that's greater than
find the equation that's what?
greater than this equation.
Which would be?
X plus 1 over x cubed plus 1.
Okay, so you want to talk about, okay, so you're going to compare this
Yes.
to x plus 1 over that, which is going to break this down into that.
And this is converged.
And how do you know that converges?
Limit.
Limit.
That's n goes to infinity.
Are you going to justify that that gives you a nice answer? What did you do at this point? How would you do that integral in general? Right? You have the integral of 1 over x squared minus x plus 1. What would the approach be here?
Partial fractions.
Partial fractions, can you factor x squared minus x plus 1? So it's not partial fractions. You can't factor that. Why'd you jump to partial fractions? What is the order? It's not a basic rule, can't simplify. Substitution is not going to work. Denominator doesn't factor, so you can't do partial fractions. What would you do? The other option. What other technique did you learn?
Parts.
By parts? What would the parts be?
I don't know, that's the only other technique we learned.
It's not the only other technique we learned.
Tricks.
Huh? It's not Weierstrass because it's not a rational trig function. So literally by process of the only one left now is trig substitution. Yeah, should have spotted that a little bit earlier, but hey, if we get there eventually, I guess it's not so fun. How would you apply trig substitution? What would you have to do to get a trig sub to apply? Yeah.
Would you complete the square?
You complete the square to get the trig sub done. So you could go that route. So first of all, what I'm liking about this, loving the fact that you guys are trying to apply the comparison theorem, because clearly that guy you would notice, hopefully if you went through all the situations in your head, we didn't cover a technique that can actually do this integral. So yes, very smart trying to compare it to something else. And you're hoping if you can compare it to something bigger and that converges, you'll be able to say the original converges. So that's a good idea. But I don't think this guy in particular is the guy you want to compare it to. That guy's a lot more annoying than he has to be. I'd probably compare it to someone else. So comparison theorem is where your head should be at, because that we don't know how to deal with that actually. And yeah, so I probably want to compare it to anything else. Can you think of something nicer to compare it to? Yeah.
Could you do it to x? Could you use it? Never mind. Could you use the same one? Would that be allowed or no?
Use the same one.
Use the same numerator. Or use the same denominator as the numerator. You can't do that, right?
Yeah, I don't think that's gonna make anything easier because then I'm gonna have to get an x cubed up here. I'm gonna have to like add and subtract an x cubed, and when I factor that off, that's gonna give me an x cubed in the top and an x cubed in the bottom. Yeah.
Could you do x squared for the numerator and then use u sub? For
And x squared, if I put an x squared in the numerator, how is that gonna change things?
could you do u sub where 3 cubed?
Yes, but in terms of the comparison theorem, what ways the inequality is gonna turn? If I replace the numerator with an x squared, am I getting something bigger, something smaller? Because I need to know that in order to apply this theorem.
Something bigger, right?
Is it?
Not unless it's less
Oh,
than
yes,
one.
Right. You have an issue between 0 and 1. If you replace this with x squared, it's actually going to be smaller on the interval 0 to 1, but larger on the interval 1 to infinity. So could kind of apply that to get a substitution in there, but you kind of would have to break the interval up. In fact, probably what I would do is break the interval up anyway, and I wouldn't quite do that idea, but I would end up doing something similar. So I would break this up from 0 to 1, and hopefully when you see how we'd approach this, you're going to appreciate why I decided to do this. Now you're all thinking of making this integral bigger by making the numerator bigger, but I would submit to you that's not the only way to make a fraction bigger, is it? Is there another way to get something bigger?
Denominators.
Make the denominator smaller would probably be something you'd want to consider. If I can make the denominator smaller, what do you think would?
X squared plus 1, or x plus 1.
It's a
Still too complicated.
Subtract the one.
Get rid of the 1, right? Because look at what would happen if this is just x squared over x cubed. That's super simple. That's a power rule, right? Why are you putting yourself in a situation where you're going to need like a trig sub and like some complicated thing? Try to do something that gets you something nice, something simple. Now you should start to appreciate why I wanted to break the interval up, because now, with just an x cubed in the denominator, having a 0 presents another bad point. But if I break it up so that there's a 1 here, 0 is not a bad point. So I'm not going to have to think about more bad points. Now this part, as far as we're concerned, that's just going to be a number. It's going to be some number, right? So this part is just going to be some constant, right? That's going to be the area under the curve, right? From 0 to 1. Function is an undefined, we can find that. Even if we can't calculate that by hand, I know that we can approximate it with Riemann sums or some other such thing. Now when it comes to this guy, if I take away the 1 in the denominator, this is bigger or smaller than the original?
Bigger.
It's bigger, right? You can make a fraction bigger by making the denominator smaller. So don't like put yourself in a box here. So this is just going to be some constant plus something like that, which is 1 over x squared, and this is now bigger. So yeah, I'm thinking the comparison theorem, I broke it up because I don't want to have to worry about 2 bad points now instead of 1, because I know I'm actually going to want to make the denominator smaller here. And why? Because making the numerator bigger puts us in trouble. I have to use a trig sub or something complicated. The easiest thing to do to make this larger is to make the denominator smaller. So that's the first thing. Should be aware that there are 2 ways to get a fraction to be bigger. Make the numerator bigger or the denominator smaller. And in general, you're going to want to try to go with the way that's going to make your life easier. And I just broke it in two to make that a valid option. Now what can you tell me about this guy?
Convergence.
That one converges, and I don't really have to do the calculations for that because by theorem that converges, right? This guy is a 1 to infinity of 1 over x to the p dx, where your p is larger than 1. We know that that converges, right? So ultimately, what we can say is this integral converges, right, and this is equal to the original integral. Converges by the comparison theorem. Because I just found an integral that's bigger, it's bigger than that integral, and it converges. And these guys are always positive once my x's are positive. So yes, comparison theorem, but if you want to finagle something algebraically, go with the easier thing. In this case, it was much easier to deal with the denominator than it was with the numerator. What about that one? Ideas?
Move the sine square x
How? What would you do with
to
it?
make it smaller, I think.
Okay. How can you make sine squared x smaller? What's smaller than sine squared x?
Because sine squared is between the domain of -1 to 1.
Sine squared is not between -1 and 1. What's sine squared between? What's a lower bound for sine squared? Sine is between -1
It's
and 1,
0.
right? Sine of x, that's between -1 and 1. Yes. If I have a sine squared,
So it's 0.
Oh, 0 to 1.
0 to 1. So it means if I wanted to make the numerator larger, I could just replace the sine squared with 1. If I wanted to make the numerator smaller, I could replace it with 0. Now, depending on which one you want to do, which one you replace it with is going to depend on what kind of result are you kind of looking out for. So, if you get something bigger, you need it to converge in order for this to converge. And if you get something smaller, you need that to diverge in order to get this to diverge. So who you replace it by comes down to, do you think it's going to converge or diverge? So what do you think? What would you guess here? Yeah.
Diverge.
You're guessing diverge. Why would you guess diverge?
Because p
Right, because it kind of looks like a constant over x to the something where the p is less than 1, right? This is just, if I replace the sign with a constant, I get a constant over x to the half. So I'm guessing based on this theorem that I know that it's going to diverge. So the one I would want is the smaller one. And so probably what I would do in that case is I'm going to replace the sine squared x with 0 as opposed to replacing it with a 1. So now notice that this guy, 1 to infinity of 1 over the radical of x dx is smaller than this. And this guy diverges by theorem since p is smaller than 1. This means that this integral here diverges by comparison theorem. That's our answer. That one diverges. That was good?
Question?
Yes.
Do we have to say where diverges to?
No, diverges just means it goes off to infinity. In this case, it goes off to infinity or the limit does not exist. So saying it diverges to something,
And we don't have to say where converges as well, right?
no, because if you're applying the comparison theorem, chances are you don't know what it's going to converge to. The most you can tell is give an approximation for what it converges to. You can give like an upper bound, but you're probably not going to know it for sure.
Okay.
The only situation where you can know for sure that it converges to is if you actually directly compute the integral, like we were doing in previous examples. But yeah, so the comparison theorem, the power of that theorem is it allows us to not directly compute these integrals. Because again, we don't have a technique that can deal with that guy. So directly computing the integral shouldn't be where your mind is thinking. You should be thinking, I need to replace it with something simpler that I can compute, and then use that to judge. And the comparison theorem gives us two options. Find something bigger that converges, and it means the original converges, or find something smaller that diverges, and the original is going to diverge as well. So that being said, what would this one look like? So the first thing to worry about is what is making this undefined?
0.
0 is the problem. 0 is the bad point here. So your sine of x isn't defined everywhere, but where it's undefined is where the cosine of x is 0, which means it's going to be undefined at pi over 2, 3 pi over 2, and pi over 2 is actually larger than 1, and minus pi over 2, the next place would diverge is smaller than 0. So our secant is actually fine on this interval. So the only thing that's a problem here is the division by 0. So the 0 is a problem. It's now a situation because of the 0 limit. Now, in terms of finding the integral of that guy directly, yeah, we don't have a technique that can deal with that. So we want to use a comparison theorem. How do we get it done? So, I guess similar to the other guy, what's especially making this complicated is the trig function.
Yeah.
So, is there a relationship similar to this that applies to the secant that we can apply here?
Can I use a negative number to replace secant square x? Because secant square is always more than 0.
No. And why is that?
Why?
You tell me. Like, once you replace it with a negative, it's automatically wrong. Like, why though?
Wait, what did you say?
His idea was replace the secant with a negative number, so it's automatically going to be smaller.
Square root of a negative.
No, that's not the issue, because secant x can be negative even when the x itself is not negative. But why is replacing with a negative thing going to be an issue?
It's an even function.
When you square it, it's automatically positive.
Yes, it's automatically positive because it's squared, but also at the same time, like replacing, like making the integral negative is a problem in general. Because what are you trying to apply here? The comparison theorem. How does the statement of the comparison theorem go?
It's less than something. It's less than something that converges to convergent. If it's greater than something like that.
No, that's not the complete theorem.
It's zeros.
Right. It says 0 is bigger than that, then this is bigger than that, bigger than that. It turns out for the comparison theorem to actually work, the greater than or equal to 0 part has to be there, right? That's how we can get the lower bound part of the comparison theorem. Because technically, you could have something diverging to negative infinity and still having the bigger one converge. But if you force this requirement, that is no longer a possibility. So having negatives in general is not good for the comparison theorem. It only applies when you're looking at positive things.
How about 0?
Right, replacing it with 0 How is that gonna help? You're gonna have the integral of 0. Like how are you gonna apply that?
It's like 1.
1? How does secant compare to 1?
1 is greater.
1 is bigger than secant?
No, sometimes equal.
Sometimes equal, so it's bigger than or equal to? No.
Oh, secant is infinity. Can
Right,
infinity and
secant is
negative
1 over
infinity.
cosine. So
Yeah.
remember,
Right.
your cosine looks like this, right? And what is the secant? Well, it's going to be undefined everywhere your cosine hits 0. So this is going to be a bad point for secant, that's going to be a bad point, that's going to be a bad point, that's going to be a bad point. Now, whenever your cosine hits 1, what is your secant? It's also going to hit 1, right? Because it's just 1 over cosine. But what happens if your cosine is something else? Then you take 1 over that number. What happens when you take 1 divided by a number that's approaching 0?
Infinity.
It goes off to infinity. Your secant graph actually looks like this, right? And of course, when you square it, you only get the positive part. So if you're looking at your secant squared graph, that's going to look like this, 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 where they're asymptotic to the odd multiples of pi over 2. So in fact, 1 is a minimum for secant. So your secant is actually always larger than or equal to 1, which also means that your secant squared is larger than or equal to 1.
I mean, like, this integral is always bigger than secant square integral.
Right, so how do you want to get this replaced?
Then we can integrate secant square to see it's converge or diverge.
So who are you comparing it to, and what side is it going to be on?
Like secant square x.
You want to compare this to the integral of secant squared x?
Yeah.
On 0 to 1?
It's
And
smaller
who's-
than the original one.
Is it always smaller?
Yeah, because the number divided by
This is the
is
integral,
smaller than 1.
not the.
It could be equal, because when it's.
Yeah, smaller
Okay.
or equal.
But, alright, but can you do that? That's actually going to converge, right?
Yeah.
Because the integral of that is tangent. So you're going to get tangent of 1. So this is going to be equal to tangent of 1 minus tangent of 0. Does that help?
No.
No. You found something smaller that converges. Comparison theorem doesn't help you.
But if you apply 1, that you will find a divergence which is smaller than the original one. That works.
So, because of this,
Yes.
if I replace the secant with
1.
Then you
with
get
1,
smaller than divergence.
I get something smaller than that.
Yes.
Now, how do we know that this guy diverges? Well, that is just
X to like 3 halves, right?
Yes.
x to the minus 3/2, which of course you get x to the, add 1 to the power, you get minus 1/2, which gives you 1 over radical x. Divide by the new power, and you get 2. Now, of course, here, what you're going to have is technically there's an n down here and a 1 up here, and the limit as n is approaching 0, blah, blah, blah. But either way, you're going to get this diverges.
It's smaller smaller diverges than.
And it's smaller, it's diverging, it's a positive thing that's smaller, so it's also another thing that's important to the theorem. It's positive, it's smaller, and it diverges. This means the original diverges. By comparison theorem. So the comparison theorem is a very powerful theorem. It allows you to talk about improper integrals without ever having to actually do the integral. But at the same time, it is going to take you some practice to know how to apply the comparison theorem in various situations. So you should know you can make things bigger by making the numerator bigger or making the denominator smaller. You should also know oftentimes when you see a trig function, your goal is going to be to replace that trig function with a constant. You should also know everyone needs to be positive for you to apply the theorem. You should also know you need something smaller that diverges or something larger that converges. And if you can't get into that situation, then the theorem doesn't work. So there's someone raising there.
Yeah, I have a
Yep.
question. Like, you just need to know, like, you just have to know this by heart, the whole thing. Secant squared is greater than 1, secant squared x is greater than 1, greater than 1. You just have to know those rules. Alright.
Or more specifically, you need to know about sine and cosine. Like once you know about sine and cosine, you know about everybody else.
Just 1 over.
So when you want to worry a secant, what am I going to do with a secant? Think of it as 1 over cosine, right? And if the maximum your cosine is 1, but it gets smaller, then it means that if you flip that, you'll get something larger. So that's what indicated that I can replace the secant by 1 and get something smaller. So yeah, hopefully you'll get a lot more practice on that stuff. Because yeah, comparison theorem does simplify your life, but applying it, there are nuances to applying it. So you want to be aware of what these nuances are and just know how to deal with special cases. Of course, realize sometimes you have to break an integral in two to get the limits to behave. Sometimes you replace things with constants. The integrals have to be positive in order for you to apply this. And yeah, you can make the numerator larger or denominator smaller to get something to fit and do whichever one's easiest. That being said, I want to move on to the next section, which is going to be based on the handouts that I gave you guys last time. We're going to do that. And yeah, after this, I think this is pretty much the last topic that's going to be dealing with integration directly. Right? So from now on, we're going to kind of move on. You might see an integral from here and there, but this is the last section about, this is directly all about integrals, right? Integrals are important, we just need to know how to compute them in various situations. And right now we know about how to compute them in various situations. But the idea is, if all those situations fail, if none of your techniques work, and you're not in a situation where the comparison theorem is going to help you, you talk about your integral. Yes?
Can I get one of those handouts, please?
Right? So if all of the if everything I've taught you fail, what do you actually do? Right? What is your last resort? Which, it's funny, in math class it's the last resort, in the real world it's actually the first resort. Like in the real world, if you have to compute an integral, no one actually tries to do it by hand. Right? Only math people try to do that. But if you're an applied mathematician or you're some sort of scientist and you would often be in a situation where you need to figure out some integral, chances are you're going to use techniques similar to what I'm going to talk about here. And so we're going to talk about, it's called approximate integration. You might hear some people refer to it as numerical integration. And this is just computing an integral straight up by computational brute force. Like, we're not going to try anything fancy applying any formulas. We're literally going to like, let's construct a bunch of rectangles under this thing and add up all the areas, right? Now, we've seen some techniques here already in Calc 1, right? So you would have seen in Calc 1 like the left-hand rule. And you would have seen the right-hand rule. And you would have seen the midpoint rule already. And the idea was kind of the following. You have some curve. It's on some interval AB that you care about. You dice it up into subintervals, they were called. The width of each of these rectangles was delta x, where your delta x was b minus a over n, where n equals the number of subintervals. And basically what you did was you constructed rectangles under these subintervals. So when it's the left-hand rule, you construct the rectangles by taking the left side to create the height of the rectangle. The left side creates the height, left side creates the height, left side creates the height. And so basically now you add up the areas of these rectangles to get approximate the area of the curve. And the idea was the more rectangles you use, the better your approximation. And you label the left endpoint x0, the right endpoint was x sub n, and then you kind of have x1, x2, so on in the middle. And basically the area here was approximated by delta x times f of x0 plus f of x1 plus da da da, all the way up to everyone except the right endpoint, so this stops at f of x n minus 1, right? You kind of add those all up, that was your left-hand rule, right? The left hand gave you all the heights of the rectangles. Cover that in Calc 1, not really going to go into much detail here, just want to jog your memory and remind you a little bit. In the right-hand rule, the same idea applied, except this time, the right side of the subinterval determined the height of your rectangle. So you have a bunch of those. You added up those rectangles, and that approximated the area. This was approximately equal to delta x, right? Which is kind of like length times height for all these rectangles. In the right-hand rule, you started at x1, then x2, and you went all the way up to the last one, f of x n. You could approximate the area that way. The midpoint used another kind of idea. First, you slice it up like that, but then you went and you took the middle of the subintervals. So you picked a point exactly in the middle here, call that x1 star, and then this one here was called x2 star. This here is called x3 star, and so on and so forth, right? And the middle is what determines the height, right? And the idea is sometimes the right hand would give you a bigger answer than you want, then the left hand will give you a smaller answer than you want, and the midpoint was kind of a way to, sometimes it gave you an underestimate, but sometimes it balances out by giving you an overestimate. So the idea is this guy is going to get to an answer quicker than the other guys. That was the idea. And now, in practice, you would have a computer help you here, and you won't use like 4 rectangles like we have you do by hand. You're going to use thousands of rectangles. And so you might wonder, why is the difference in variation? Like, why do we even need this if a computer is going to do the work anyway? It turns out that, and I don't know if any of you are going to have experience with computer science at some point, computing power is no joke. It's not something you want to squander. If you have a method that by hand it's easier for you to do, then eventually it will be easier for a computer to do. And so, yes, the computer can do thousands of calculations, millions of calculations, but if you make those small calculations harder than they have to be, even the computer is going to run into issues eventually. It won't have enough memory or computing power to actually get it done. So it's very important for you to have a different variety of situations for you to tell the computer, oh, in this situation, try this method. In this situation, try this instead. Because if you try this method, you're going to run out of computing power. So you have to have an understanding of what would be entailed in each method so that you'd be able to properly program a computer to deal with different situations. Because computing and power is a major issue. So we had a bunch of ways to do that, and of course this one uses the midpoints here. A is going to be approximately equal to delta x times f of x1 star plus f of x2 star plus da, 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 f of xn star. Right? So these we all saw in Calc 1. Now we are going to try to come up with more refined methods than even these. So these guys were some of the ways that we could use rectangles to approximate the area. Now what we're going to do we're going to learn how to use trapezoids and parabolas. And so we're going to talk about two new methods. So these you would have seen already in Calc 1, and I do expect you to remember how to set one of these guys up. But for now, we are going to talk about two new methods. So we have the trapezoid tool. You'll see the formula on the handout that I gave you. The idea is the following. I have some function I want to approximate the area under it between A and B for whatever reason. So I'm going to split this up into a bunch of subintervals. Now here's how we're going to actually calculate the subintervals. Instead of erecting rectangles, the idea is we think it will fit the curve a lot nicer if you just use trapezoids instead. Just have the endpoints of these guys connected with a straight line, right? If you use a rectangle, you're going to actually miss that entire area or be overestimating by that entire area. Whereas if you use a trapezoid, the error is just that little bit of area right there, right? So we kind of just connect these points and then connect them with straight lines. And so what we create is not a bunch of rectangles, but instead a bunch of trapezoids. And so now the area is just going to be the sum of the area of these trapezoids. But how do you figure out what that would actually look like? Well, again, these are all delta x. And does anyone remember what the area of a trapezoid is?
It's the average. It's the average of the bases times the
Distance between them, right? So if I said this is, say, x1 comma y1, and that's x2 comma y2, that's x3 comma y3, and that's x4 comma y4, then the area of the first part is going to look like, well, it's 1/2 times y1 plus y2 times the distance between them. The area of this is going to be 1/2 y2 plus y3 times the distance between them. The area of this is going to be 1/2 y3 plus y4 times the distance between them. You'll notice that I'd be able to factor out a delta x over 2 as a common term. And if I combine these, I would have a y1, I would have two y2s, I would have two y3s, and then a y4. And that kind of tells you where the formula for this comes from. It's going to be delta x over 2 times f of x1 plus 2 f of x2 plus 2 f of x3 plus is going to double up on all intermediate values and then add the last one. And that's that formula right there. Your delta x is the same thing, the same b minus a over n. And, but instead of adding all these guys, so this is the, notice here, I want you to notice that you first start evaluating at the left endpoint. And then this is the right endpoint. And you double all the y values in between, multiply by delta x over 2. That's your approximation with trapezoids. Now, we're going to stop there. Next time, we're going to learn how to actually do this with parabolas, because that will actually fit a curve even nicer, is the idea. So you can actually try to apply this formula to calculate some things. We'll definitely get through that next time. Next time, we don't have class on Tuesday. Right, because Tuesday is a Monday schedule, so the next time I'll see you guys is Wednesday.
So we won't have
We won't
quiz
quiz, right?
next week, right?
No quiz.
Okay, I'll give you guys a break next week. But yeah, so next time I'll see you guys on Wednesday. Actually try some of these things. Like you can just use the formulas. I'll explain to you where they came from, but technically you don't need to know where they came from in order to do the problems. We'll pick up with that on Wednesday.